Hi everybody, welcome to another video in Differential Equations, section 2.2, Separable Equation. Starting from this section, we actually learn how to solve differential equation. But the most important things in differential equation when we solve them is that we just need to know that they have to be in some certain forms, because in certain forms they have different type of solution. Right, so this is the first example of that separable equation. So how do we distinguish separable equation with the rest of other equation? Right, so separable equation is in this case is the first order equation. So we only have derivative. So the left hand side is the derivative. The right hand side, of course, is a function of x and y, but very special way. The function on the right can be expressed as the product of g of x. When we write g of x, we mean only depends on x. And then p of y, then there's a reason we choose p instead of g. That only depends on y. So whatever the function on the right hand side is the product of a function of x times the product of a function of y. So there's no mixing between x and y. So that's why we call this equation separable equation, because the function can be separate as a function of x times the function of y. Right. For example, the equation y prime equal to e to the x sine y is a separable equation, because we can write e to the x is a function of x times sine y is a function of y, derivative equal to a separable function. So yes, this is separable equation. This derivative equal to x squared plus 2y. We cannot write this as a product of a function of x and times a function of y. So this is not separable, because we cannot write that as a product of a function of x times the function of y. This one can. Right, so pretty straightforward. The separable equation, we have derivative equal to a separable function. Pretty much that. Right, let's look at some example. Determine if the following equations are separable. So we have the first example here. Is that separable? We have derivative equal to the function on the right hand side. So can we write this as a function of x times the function of y? Right. If we rewrite, both of them have x, so why don't we factor out an x on the top? Now we have x times 2 plus y over y squared plus 1. We can write this as x times 2 plus y over y squared plus 1. So we have a function of x times a function of y. So yes, this is separable. Right. We will learn how to solve this equation later, but for now, that's all we have. Next, is this equation separable? At first, no. But when we look closely, this is e to the x plus y, e to the x plus 2y. We use these properties. And we can rewrite that as a product. Multiply two things with the same exponent. Multiply two things with the same basis. We can add the exponents. So that's what we have here. So we'll rewrite this as a product e to the x times e to the 2y. We use this formula more than a few times. Right. And a function of x times a function of y. So yes. So this one also separable. Right. So simple enough. Next, we have derivative equal to this. 1 plus 2x cubed times y. cannot factor, cannot do anything. So this one is not separable. Right. The other two are. Right. So from now we know how to determine if the equation is separable or not. Now, how do we solve a separable equation? Right. Very simple. If we have differential equation where the right hand side is separable equation, I will rewrite this as h of y 1 over p of y. So we can write like this and we turn the equation to this. But what is this? Right. So the point here is you see we have y on one side and x on one side. So that's the idea. Separable equation, move x and dx on one side, y and dy on one side, and then integrate. And that's all there is to it. So the first step is separable equation, right? So we separate x with dx from y and dy, or y with dy. So yeah, keep x and dx on one side, y and dy on one side. Yeah, and then the second step we just integrate both sides, and that's it. Yeah, right, and that's all there is for this section. And now we just do a bunch of examples. Right. Look at the first example. This one has the solution. So what we have is dy over dx is x minus 5 over y squared. So cross multiply. We have y squared on this side with dy, x minus 5 with dx on the other side. Then integrate both sides. Integral of y squared is y cubed over 3. Integral of x squared over 2, 5 minus 5x. And don't forget, when we integrate, need to put a constant on either of those, on one of the two sides. Usually I put it on the right hand side. Alright. Now if we want to solve for y, by the way, when we integrate, we can say this is an implicit solution. So that is implicit solution. So we have the equation relate y and x together. If we want to multiply 3 on both sides, when we multiply by 3, we have 3c here, right? But since c is a constant, 3 times c is still a constant. So that's why I still write c. Because since 3c is a constant, I will make that equal to c. And then we take the cube root on both sides. We have y equal to that. So this is the explicit solution. Right, so simple enough, right? So like I said, first step is x with dx, y with dy, and then we integrate both sides. So there's no formula, nothing. And of course you just need to know how to integrate. Right, next, solve the following equation and write the solution in implicit form. So we write this equation for this in implicit form. Don't need to solve for y. Right, first, to get y on one side and x on one side, cross multiply. So we have cosine of y plus e to the y on the left hand side with dy. So when we cross multiply, that's what we have. And then multiply dx on the other side. 6x fifth minus 2x minus 1. Right, and now we just integrate. So separate x away from y. So x on one side, y on one side, integrate. So that's all there is to it. The concept, pretty simple. Right. Integral of cosine is sine. Integral of e to the y is still e to the y. We can plus a constant on the left hand side, but usually I put a constant on the right hand side. Integral of x to the 5th, x to the 6 over 6. Integral of x, x squared over 2. Integral of 1 is x, and then there's a constant. Right. 6 and 6 cancel out, 2 and 2 cancel out. So we have sine of y plus e to the y equal to x to the 6 minus x squared. Except if I copy the problem correctly, this is a plus, right? So, sorry. So that's a plus. Right. So that's what we have. Very straightforward. So the concept is pretty simple. The problem complicated or not depends on the problem that we have to integrate. Could be complicated. Depends on the integration. Right. Next we do this one. If we don't have enough space, there are a few lines on the next page. But usually if the problem is a little bit long, I will cut the page in half. So. Right. So this we solve for the initial value problem. Initial value problem is where we have the initial condition in addition to a differential equation. Right. So simple enough. This is still a separable function, right? A function of x times a function of y. It could be multiplied, it could be divided, it doesn't matter. But the point here is we can bring x and y on one side by just cross multiply. Right? If we cross multiply, the y minus 1 will go down here. We have 1 over y minus 1. And then move the dx on there. So we have 1 over x plus 3. And then where's the dx and dy? Right. Move the y minus 1 here. So there's dy. And move the dx over. So yeah, that's what we have. Right. Cross multiply. In fact, let's just cross multiply first. So we have x plus 3 times dy equal y minus 1 times dx. Yeah, that's cross multiply. And then we move the y minus 1 down and x plus 3 down. That's what we end up with. Right, so cross multiply x plus 3 times dy, y minus 1 times dx, and then move the y with the dy. We keep the dy and dx on itself. We don't move those. We move everything else. So the y to this side, the x to that side, and that's what we have. Now we integrate both sides. Right. I don't know how to use, how do you integrate in calculus 1, but what I do is I use substitution. If this is 2x or 3y, something like that, it will be a little more complicated. So I will use substitution. And the substitution is let something equal to u, and I'm going to solve for dy, dx or dy. So what I do is let u be y minus 1. So we have the bottom there, and we'll find derivative of this. Derivative of u, du over dy is equal to derivative of this with respect to y is 1. Move the dy over, so du is equal to dy. So that's what we have. For that substitution. For the other substitution, we do similar thing. Let v be x plus 3. Take derivative dv over dx. Derivative of this with respect to x is 1. Cross multiply So dv is equal to dx. Right. Now with that, we substitute into our problem. Integral 1 over y minus 1 is going to be u, and du is dy. So we have 1 over u, dy is equal to du, equal to 1 over x plus 3 is v, dv is dx, or dx is dv. Right, integral of reciprocal function 1 over u, so it's going to be ln of absolute values of u, and we have ln of absolute values of v, plus a constant c. Right, so that's good and all, right? U is y minus 1. And v is x plus 3. So that's good there. Now the question is, how do we get rid of the ln? So the natural log is the inverse function of exponential function. Namely, the properties that we use here is, I'm just going to put that here, e to ln of something, let's say m, e and ln cancel out, is going to be m. So when we want to get rid of the ln, raise both sides as a power of e. Notice the c is on the exponent as well. Right? Now the e and ln cancel out. Now, before we do that, the e and ln cancel out, but what happened to the plus c? Well, we cannot do that. But we did have that properties earlier, right? And I did say that we use this more than a few times. So we use that properties. Notice that this is plus here. So I will cancel out later. Actually, like right now, just cancel them. E and ln cancel out. We have absolute values of y minus 1 equal to. Now we have addition on the exponent. We can write that as a product. Right? Now the e and the ln will cancel out. So that gives us absolute values of y minus 1 equal to. By the way, what is e to the c? C is a constant. E to the c is still constant. Actually, any function of c is also a constant. So e to the c is constant. Right? E to c is still constant. So we just give that equal to another c. Just make that equal to. So I usually use the column equal to, meaning we make that equal to something. It's not just equal to, we make it equal to c. So that will be c times everything e and ln cancel out too. We just have absolute value of x plus 3 times the constant c. So I have the constant c times the absolute values of x plus 3. Right. Now, how to get rid of absolute values? Right. So, then ask you a different question, right? What is, if absolute values, don't worry, we have space on the next page. That will be enough. So if we have let's say a absolute values of a equal to u, and when u is positive or at least 0, then what's a equal to? So a will be equal to u or negative u. Right. So in that case, we can drop the absolute values on both sides, and I would throw in the plus or minus in front of it, right? So if we drop the absolute values, we can just throw in the plus or minus on either sides. So we can say y minus 1 equal to, when we drop the absolute values, we can just say plus or minus on one side when we drop both absolute values on both sides. I just use the parentheses. Right, that's where we drop the absolute values. Now, I did mention that c is a constant, right? E to the c still constant. Plus c minus c still a constant. So whether we have plus or minus c is still a constant. So we still make that equal to c. Right? So usually, just like in Cal 1, if we have a constant, we just write c instead of plus or minus c or e to the c or something. It doesn't matter. Right. I did mention that we have space on the next page, so we can continue on the next page also. Yeah. If you bring out the note and you bring out the lecture and then write directly on it, try to write small because we have a lot of things to write down. Right, so we continue from here. So plus or minus c is still constant, so we make that equal to c. So we have the equation is y minus 1 equal to c plus x plus 3. And this is what we call a general solution, because in general there's a constant c there. Actually, it is better just move the 1 over. So y equal to c x plus 3 plus 1. Actually, yeah, so that one should be a general solution. It is much better. We have y equal to, right, this is general solution. There's a constant c there, which is fine. Right, this almost everything except in this one we have the initial condition, which we haven't used. So we have y of negative 1 equal to 0, which the initial condition we haven't used. So we continue this problem. We go from here to here, here, and then here. Alright, x equal to negative 1, y equal to 0. So I substitute x equal to negative 1 and y equal to 0. So we have 0 equal to c, x equal to negative 1 plus 3 plus 1. And that is 0 equal to 2c plus 1. So c is negative 1/2. So the general solution, we have c in it. For the initial value problem, we have c equal to negative 1/2. And for that particular initial condition, we have c equal to negative 1/2. So we have y equal to negative 1/2 x plus 3 plus 1. And this is a particular solution to the IVP. With the initial condition, we have this particular solution. So that's what we have. Right, once again, we start here and continue on the next page. Right, so it's not that bad, right? Right, let's continue. Right, solve the initial value problem. Also for this, the next two problem, it is a little bit long, so I cut the page in half. Perfect. So it will fit on the screen. So that's why I do like this. It also save paper. Right. So solve this initial value problem. So first, this is a separable equation to try to keep x on one side, y on one side. First, I move the dx. And then the dy on this side, the x on that side, so move all the y on this side. So divide and then I still have just have 2x dx. So simple enough, right? Now, 1 over cosine is secant. Yeah. So differential equation, it's not easy, but the reason that is difficult because it have a little bit of everything. So like this little trick about the constant, plus or minus with absolute values, and that is a constant. Those little trick that we need to do, we need to know, and is this something that we might not learn earlier? So sometimes we have to learn, we have to do a few problems and see some certain things that we have to do, some certain things we have to watch out for, and that's why it makes it difficult. On top of that, on this you have to know all the trigonometry, all the calculus, all the derivative, all the integration. That's why it's difficult. The differential equation by itself is not the worst. It's not easy either, but it will be manageable if we have to count 1 and count 2 and all the trig function and all the things. Right, so 1 over cosine is equal to secant. And so every time we need something in trigonometry, recalc or calculus, I will write that again in the box. So like those are the things that we might need to know. Right, so that will be secant, and we have the square, so that will be secant square. And then we'll just integrate both sides. And this initial condition is a little strange. So integrate both sides. Integral of secant square is tangent because derivative of tangent is secant square. Like I said, I will write everything that we need. Integral of secant square tangent because derivative of tangent is secant square. Right. So I have tangent of y equal to integral of 2x, x squared over 2, plus a constant c. Cancel out the 2. We have tangent of y equal to x squared plus c. Right, so this is the implicit solution. We have an equation relate x and y together. Right, but this one we need initial value problem, so it's a little more than just that. So we continue. Hopefully, there's all the space we need. Right, so we continue. To get rid of the tangent, we take the tangent inverse on both sides. So we apply the tangent inverse on both sides. Tangent inverse and tangent, so y equal to tangent inverse of x squared plus c, and that is general solution. Right. Now we have the initial condition y of 0. Usually when I do math I use pencil, but it's difficult to see if I write in pencil. And more than ever in this differential equation class, the color code sometimes you have to be a little more organized so we don't confuse, because if we write everything in pencil and then we kind of difficult to follow. Right, y of 0 is equal to pi over 4, so I'm going to put x equal to 0, then y will be equal to pi over 4. So I have pi over 4 for y equal to tangent inverse 0 square plus c. Actually, it would be much better if we substitute in there, but I will get back to that and do it differently. Don't worry. We still good though. So pi over 4 is equal to tangent inverse 0 squared c. To get rid of tangent inverse, we can take the tangent. By the way, that is not always true. We have to have some certain condition for it to work. We cannot just do that every time. Right, so we take tangent on both sides. This is much better if we just put it directly here. I mean. So we take tangent on both sides. And that cancels out, so c is equal to tangent of pi over 4, which is 1, right? So once we have 1, we can substitute that back into the general solution. And we have the solution y equal to tangent inverse of x squared plus 1. Right, first I said tangent and tangent inverse not always cancel like that, because we have to consider the domain and range in the inverse function and inverse. Right, so I said there's nothing, that's perfectly right there. And this is the solution, a particular solution for the initial value problem. Right, now I did say that it would be much better if we just use this with the initial condition. So y of 0 equal to pi over 4, meaning that x equal to 0 and y equal to pi over 4. So I will substitute this into the implicit form. Tangent of pi over 4 equal to 0 square plus c. And from here we just say c is equal to tangent of pi over 4, which is 1. Which is much better than doing all of this. Which is perfectly fine. right? So that's all we have for that problem, right? So there are a few things we need to watch out for. Right, next, this equation. So first, not quite in the right form yet, but we have to shuffle. Let's move one thing to the other side. Typically I want to keep the y on the left hand side because solution at the end may be y equal to something on the right. So I prefer to keep the y on this side, the x on the other side. So y and this I will move to the other side. Right. So on the right hand side we have 1 plus x dy. So dy on the left hand side, and then on the right hand side we have negative. So we have y dx. Right. Now y with dy, x with dx. So this I have to move to the bottom, and 1 plus x have to move to the bottom as well. Yeah, just keep a minus at the bottom. Doesn't matter. And 1 plus x dx. Right, simple enough. Now just integrate. Before we integrate, it's easy to rewrite this square root of y as y to the 1/2. Move to the top, become y to the negative 1/2. And then don't forget there's a negative sign. So on the left hand side, it's still negative. Y to the 1/2 from the bottom, move to the top, negative 1/2 dy. And then on the right hand side, we do nothing to that. Right, it's good now. We can integrate. Right. The left hand side is the power rule, should be easy. The right hand side, use substitution like we did before. I'll let u equal to 1 plus x. Yeah. So this time I'm not worried about how to integrate. But this is a substitution. Right, and then we take derivative. Derivative on the right hand side of x plus 1 is 1. Move the dx over. So du is equal to dx. So we can substitute that in for dx. And 1 plus x is going to be u. Right, so put everything. On the left hand side, the integral will be easy. Just a power rule, right? So the integral of that is y increase the power by 1, negative 1/2 plus 1 is 1/2. And then divide by the same thing. Right? Power rule. And then on the right hand side, I will rewrite this integral as 1 over 1 plus x is going to be u, and dx is the same as du. So that's what we have. Right. To rewrite this, we will have divide by 1/2 is multiplied by reciprocal. So we have negative 2 y to the 1/2 equal to integral of 1 over u is ln of u. ln of absolute values of u. So don't forget the absolute values, especially in my math lab when you type in the answer, whether you're missing absolute values or not, actually it will count as incorrect. By the way, if you have a test question and then you forgot the absolute values and it count a question wrong, please take the screenshot and send it to me. I'll give you partial credit for that. I don't know why. This will be u, right? Let's see. Right, divide by 1/2. 1/2 is multiplied reciprocal, so multiply by 2 over 1, which is just 2. And that's still negative. So that's what we have here. And then u is 1 plus x. So we have y negative 2, y to the 1/2 equal to ln absolute values of x plus 1 plus c. Right. Now I will try to solve for y by itself. So divide everything by negative 2. So divide by this negative 2. And then still there's nothing wrong there. Right. Now c is a constant multiplied by negative 1/2, still constant. So we just write that as c. Negative 1/2 ln x plus 1 plus a constant c. Right. To get rid of the square root, why don't we square both sides? And that gives us y equal to negative 1/2 ln of x plus 1 plus c. So that is the general solution. With the constant c, because we haven't finished, sorry. We'll square both sides, right? So that is a general solution. Which is good. Now, initial condition, y of 0 equal to 1. So meaning that when x equal to 0, y will equal to 1. Right, substitute 0 in for x, 1 in for y. One for y and 0 for x. So we have 1 equal to ln of 1. Yeah, we have a calculator there for too long, but usually I just leave it there so we kind of fill out the screen. Yeah, ln of 1 is 0. Yeah. So ln of 1 equal to 0. So we have just negative 1/2 times 0 plus c square So c square is equal to 1. Right? If c square is 1, then what is c? Be square root of plus or minus square root of 1, which is plus or minus 1. Right? So c be equal to plus or minus square root of 1, or just plus or minus 1. And we substitute back into our problem. So we have the solution y equal to -1/2 ln of x plus 1 plus or minus 1. Square. Right. So is that correct? Now, we run out of space, but remember when we substitute in, we can substitute in this step and on that step earlier, right? I mean on the step where we have this solution. Now consider we do have this solution, right? Here, think about this. If we put in 0, if 1 here for y, and 0 in for x, ln of 1 is 0, so we have 0 plus c equal to 1 to the 1/2. So c is equal to 1. So what we learn here, although there's nothing wrong here, but I said we run out of space, there should be one thing. So keep this in mind when we see this again, because this might be potential problem. So what is the potential problem? Will be this step. Every time we square both sides, for example, this equation is completely wrong, but when we square both sides, it is true. So whenever we square both sides, have to be very careful. We need to check the answer. So every time we square both sides, we check the answer. So actually it is better just before we square both sides, we substitute the number in where we square both sides. Because whereas both sides, something like this may happen. So the answer is not plus or minus. Like I said, I'm running out of space, but the answer can only be 1, because when we check, so right, so we have to check the answer. I don't have highlight, but I don't emphasize enough. Whenever we square both sides, we have to check the answer. So I have to be very careful there. And so when we have plus or minus 1, we have to put it back in here and check. Have to check the answer. And when we check, what was that? When we check, c can only be 1. Because if you put -1 in here, it doesn't work, because y have to be positive. So c have to be positive. So when we do that, c can only be positive. So like I said, doesn't matter how good you are in calculus 1, 2 or 3, or trigonometry, everything, there's some certain things that we did not emphasize at all in trigonometry or even like this algebra. Like when we square both sides, have to check the answer. Like when we tangent and tangent inverse cancel out, but they have to have some certain condition, otherwise that will not work. The tangent and tangent inverse, the domain and range have to match. But it, I mean, tangent of something will be from negative infinity to infinity. So the domain, domain for x is only from negative pi over 2 to pi over 2. Because tangent of pi over 2 is sine of pi over 2 over cosine pi over 2 equal to 0. So this one is undefined. Right. So the domain and range. When we have in this domain and that range, the tangent and tangent inverse cancel out. If it is not in here, yeah, they won't cancel out. Just like we did earlier, where pi over 4 and 0, which is perfectly fine. Right. On this problem, when we square both sides, have to be mindful that we have to check the answer because some of them may not work. So when we square both sides, check the answer. That's a plus or minus, and only the plus will work, the minus doesn't. Because if you put minus 1 here, that one is 0, square root y, we cannot, that will not work. 1 equal to negative 1, that doesn't work. So yeah, the little things in differential equation make it a lot more difficult than it actually is. But like I said, the concept of separable equation, very simple. X by itself, y by itself, integrate. And then I think in this section we cover a few important toolbox that you need to do differential equation. We will see a lot more time. Right, that one of course. And how do we get rid of ln? How do we get rid of absolute values? How do we get rid of tangent inverse or any trig function? And be careful when we square both sides. Have to check the answer because maybe not all of them will work. For example, this before squaring both sides, totally wrong. But when we square, it works. So we have to check before it's square to see if actually it's true or not. Right. So like I said, watch out for those little things. But I will stop this section here. As always, thank you for watching.